You strap into the command chair, the engine lights. Ahead, the stars stretch into needles of white fire, and the hull begins to glow from gas you cannot see. We will ride a nuclear bomb stack out of Earth, fire a ship with a laser the size of a city, and stand at the edge of a wormhole that wants to crush us. Hit subscribe if you want the full engineering briefing. Strap in. Launch sequence starts now. You're sitting in the pilot's seat of the fastest ship humans have ever designed. The throttle is wide open, and the needle stops moving. Every engine blueprint on Earth hits the same invisible wall. Scientists call it the speed of light. Light moves at roughly 186,000 miles every second. In the time you blink, a beam of it could circle our planet more than 7 times, and nothing with mass is allowed to match it, ever. This rule comes from a confirmed theory, tested for over a century. Albert Einstein wrote it down in 1905, and every experiment since has agreed. Particle accelerators in Switzerland whip protons to 99.999% of light speed. That last sliver of a percent? Unreachable. The closer you push, the harder the universe pushes back. Imagine shoving a shopping cart. Easy at first. Now imagine the cart growing heavier the faster you run. At a jog, it weighs twice as much. At a sprint, 10 times. At full tilt, 1,000 tons. That is what light speed does to a spacecraft. The ship fights you, the universe fights you. Physics itself becomes the enemy. Here is the part that breaks engineers. To reach just half of light speed, a 1-ton probe needs more energy than the entire United States produces in a year. To hit 90%, multiply that by 50. To touch light speed, you need infinite energy. The math does not care about your ambition, yet the dream refuses to die. In 1958, the United States government funded a team at General Atomics in San Diego. Their mission sounded insane. Build a starship, fuel it with atomic bombs, ride the shock waves. They called it Project Orion, and we will walk the blast doors of that ship in a later chapter. The nearest star to our planet is called Proxima Centauri. It sits about 4¼ light years away. That means light. The fastest thing in existence takes 4 years and 3 months just to reach it. Our current spacecraft, moving at their best speed, would need over 75,000 years to arrive. A family that launched a ship the day the pyramids were built would still not be there. And this is only the nearest star. Our galaxy holds more than 100 billion. The one beside ours, Andromeda, sits 2.5 million light-years out. A round trip at light speed, if it were possible, would outlast every civilization that has ever existed on Earth. So engineers began asking a darker question. What if we gave up on light speed and settled for a fraction? 20%, 10%, even 1%. The numbers start to look possible. The timelines shrink from eternities to centuries. Then comes the second wall. A wall nobody saw coming until they ran the simulations. At those speeds, empty space is no longer empty. A single grain of dust, smaller than a speck of flour, becomes a weapon. The hull of your ship sees it coming at a speed that turns matter into plasma. That first dust grain is about to hit. And what happens next will tear the front of your ship apart. The grain is invisible, smaller than a full stop on a page, weighing less than an eyelash. And it is heading toward your hull at 60,000 miles per second. When it hits, it does not scratch the metal. It does not dent it. It explodes. Engineers at the Planetary Society ran the numbers for Breakthrough Starshot, a real project we will visit soon. Their verdict stunned the team. A dust particle the size of a pepper flake striking a ship at 20% of light speed releases energy equal to a hand grenade. A grain the size of a sesame seed delivers the punch of a stick of dynamite. A pebble the weight of a penny unleashes the force of a small tactical warhead. And space, which looks empty through every telescope, is full of these particles, millions of them per cubic mile. Your ship will plough through a storm of them every second of the voyage. Picture driving a motorcycle through a cloud of gnats, harmless at 30 miles per hour, stinging at 60. At 300 miles per hour, each gnat becomes a bullet. Now multiply that speed by 1 million. That is the world your ship enters at relativistic velocity. Every speck of cosmic dust becomes a cannonball fired directly at your face. The physics is simple and brutal. When two objects collide, the energy release depends on their speed squared. Double the speed, quadruple the damage. Go 100 times faster, and the impact gets 10,000 times worse. At light speed, the numbers run off the page. Scientists at Johns Hopkins University modelled what would happen to a standard aluminum hull. At 20% of light speed, a single grain of interstellar dust burns straight through. The metal does not slow it down. It vaporizes on contact, blasting a tunnel of superheated gas out the other side. A hole the width of a soda can, punched clean through 6 inches of shielding, and the damage does not stop at the entry point. The impact sends a shock wave through the hull, cracking nearby panels, rupturing fuel lines, shredding electronics. One grain can disable an entire sector of the ship. Here is where it gets worse. The interstellar dust is not evenly spread. Our galaxy contains thick clouds of the stuff stretching for light years. Telescopes have mapped them. The nearest one, called the Local Interstellar Cloud, surrounds our solar system right now. If a starship ever leaves home, it flies directly into that cloud on day one. The crew would not see the impacts. They would feel them. A sudden jolt, a distant rumble through the hull, a warning light flashing red, then another and another. Thousands of strikes per hour, each one a small explosion tearing at the front of the ship. Engineers have proposed solutions. Thick ice shields at the nose, 40 feet deep, absorbing the blows. Sacrificial layers of graphite designed to vaporize before the damage reaches the crew. Magnetic fields strong enough to deflect charged particles before they strike. None of them have been built. All of them add tons of weight, and every extra ton of shielding means more fuel, more engine strain, more years added to the journey. The dust, though, is only the opening act. Because hydrogen, the lightest atom in existence, is about to become the most dangerous thing on your ship. The crew expected dust. They prepared for it. What no one warned them about was the air. Space is not a perfect vacuum. Floating between the stars, spread so thin it looks like nothing, sits a ghost of gas called the interstellar medium. In every cubic inch of deep space you might find one hydrogen atom. Lonely, drifting, harmless. At walking speed, a hydrogen atom has the punch of a falling snowflake. You would never notice it hit you. Your skin stops trillions of them every day on Earth without you feeling a thing. At relativistic speed, the equation flips. That same atom slams into your hull with the force of a high-energy bullet fired from a particle accelerator. Scientists at the Harvard-Smithsonian Center for Astrophysics calculated what happens next. At 20% of light speed, hydrogen atoms strike the ship with the energy of X-rays. At half of light speed, gamma rays. At 90%, the radiation pouring through the forward hull matches the inside of a nuclear reactor during meltdown. Picture standing on a motorcycle in a rainstorm at 90 miles per hour. The drops do not fall on you. They stab you. Now take that same rain, shrink each drop to the size of an atom and fire it at you 1,000,000,000,000 times faster. The rain becomes invisible fire. Your skin becomes the target. That is what the front of a starship faces every second of cruising speed. A continuous hurricane of atomic bullets, each too small to see, each carrying enough energy to break molecules apart on contact. The damage is twofold. First, the atoms punch through the hull and cook the crew with radiation. A human body exposed to that kind of gamma flood dies within hours, not from heat, from the slow unravelling of every cell inside them. Second, the hull itself begins to change. Hydrogen atoms smashing into aluminum or titanium at those speeds do not simply pass through. They embed themselves in the metal. They transform the atomic structure. Over months, the shielding turns brittle. It cracks. It flakes. A hull that launched from Earth strong and whole arrives at its destination looking like sun-bleached paper. And here is the cruel part. You cannot steer around it. The hydrogen is everywhere. Every cubic mile of the galaxy contains the same ghostly mist. There is no clear lane, no safe corridor. The faster you fly, the harder it hits. A team at the University of Hawaii proposed a solution they called the magnetic scoop shield. A bubble of powerful magnetic fields projected ahead of the ship, bending the incoming atoms around the hull before they strike. On paper, it works. In practice, the energy required to generate that field at relativistic speed exceeds the output of a small star. Another team suggested flying the ship backward, using the engine exhaust itself as a forward shield. A clever trick, except the exhaust thins with distance and the atoms keep coming. Every design leaves the crew exposed. Every calculation ends with the same warning written in red ink. Radiation lethal, hull degradation severe, mission failure within years. The crew is already dying, and the ship has not even reached half of cruising speed. Meanwhile, something stranger is happening to the clocks on board. You check your watch. 6 months have passed since launch. Down on Earth, your daughter has graduated college, married, and buried both of her parents. This is confirmed physics, tested thousands of times. When you move close to the speed of light, time on your ship runs slower than time on Earth. Not as a theory, as measured fact. Scientists have placed atomic clocks on airliners and watched them tick slower than their twins on the ground. The effect is tiny at jet speed. At starship speed, it swallows lifetimes. The math is unforgiving. At 90% of light speed, 1 year on board equals 2 years back home. At 99%, 7 years pass on Earth for every 1 year you experience. At 99.9, the ratio jumps to 22. Push to 99.99, and a single year in the ship costs 7 decades on the ground. A round trip to a star 10 light years away, cruising at that speed, would feel like 3 or 4 years to the crew. They would return younger than their children. They would step off the ship and meet grandchildren older than themselves. Every friend, every sibling, every dog they left behind would be dust. Picture sending a letter that takes 70 years to deliver. You write it as a teenager. Your best friend reads it as an old man. That friend writes back, and the reply reaches you 10 minutes later, while you're still 17. The two of you are no longer in the same world. You live in different centuries separated by an engine. Scientists at the European Space Agency call this the loneliness problem. Every psychological model of long-duration cruise assumes a connection to home. Letters, messages, the knowledge that someone is waiting. At relativistic speed, that connection dissolves. The crew does not travel through space alone. They travel through time alone. Here is the part the training manuals skip. The crew cannot feel the distortion. Their watches tick normally. Their hair grows at a normal pace. Their bodies age the way bodies age. Inside the ship, everything looks fine. The wound only shows when they come home, and everyone they ever loved is gone. One proposed solution involves sending a second ship behind the first, carrying families and friends on the same relativistic schedule. An entire culture moving together through time, cut off from Earth but connected to each other. The engineering cost doubles. The social cost might be worse. A whole civilization, born into the voyage, knowing nothing of the planet that launched them. Another proposal studied at Princeton University suggested cryogenic sleep to bridge the gap. Freeze the crew, let them skip the lonely years, wake them at the destination. The problem, which we'll reach in a later chapter, is that no human body has ever survived the freezing process intact. And time dilation is only the beginning, because as the crew keeps accelerating, the light from the stars ahead of them starts doing something no textbook prepared them for. The stars turn blue, then ultraviolet, then something that kills. The windows at the front of the ship are darkening, not because the stars are fading, because the stars are getting brighter in a way that human eyes cannot see. The light pouring in from ahead is changing colour. Yellow stars turn white. White stars turn blue. Blue stars turn into something the pilots have no word for, a glare that fries cameras and melts coatings. This effect has a name and a century of confirmed physics behind it. Scientists call it relativistic blue shift. When you fly toward a light source at high speed, the waves of that light get squeezed. Shorter wavelengths, higher energy. The faster you go, the harder the squeeze. At walking pace, the effect is nothing. A police siren sounds higher pitched when it drives toward you, then lower as it drives away. Same principle. Sound waves bunching up in front of the car, stretching out behind it. Light does the exact same thing. At 20% of light speed, visible starlight shifts into ultraviolet, the kind that burns human skin on a summer afternoon. At half of light speed, it shifts into X-rays. At 90%, gamma rays. The entire forward view becomes a wall of radiation hotter than the core of a dying star. Picture walking toward a campfire, warm, pleasant. Now run at the fire. The warmth grows stronger. Now sprint at it at 1,000 miles per hour. The warmth becomes heat. At 10,000 miles per hour, the heat becomes flame. At light speed, the flame becomes a blowtorch aimed directly at your eyes. And the heat is only the surface problem. The energy carried by blue-shifted light punches through windows, through hulls, through skin. A team at the California Institute of Technology modelled a starship cruising at half of light speed through an ordinary stretch of the galaxy. The forward shielding absorbed more energy per second than the output of a small power plant. Every minute enough heat to boil a swimming pool, every hour enough to melt steel. The crew inside would not see the damage at first. They would feel the cabin growing warmer, the air conditioning straining, warning lights blinking yellow then red. Then the forward cameras would fail, one by one. Then the heat shields would start to glow. Then the ship would cook from the front backward, like a loaf of bread in an oven. Scientists have proposed thick domes of lithium hydride at the bow, absorbing the radiation before it reaches the crew. The dome works. It also adds hundreds of tons of weight. Every ton forces the engine to burn more fuel. Every unit of extra fuel forces more shielding. The design spirals. Another team proposed spinning the ship so no single surface faces forward for more than a second at a time. A clever trick. except the bow-facing surface still cops the full blast just in rotating shifts. The damage averages out. The ship still burns. Here is the part that makes engineers quiet. The blue shift gets worse the faster you go, but going slower takes longer, which means more years inside the ship, which means more radiation damage, which means more shielding, which means more mass, which means slower acceleration. Every solution feeds the next problem. The forward view, though, is about to do something stranger than any crew has ever trained for. The stars themselves are about to disappear. Look out the forward window. The stars are gone. Not dimmed, not shifted. Gone. Replaced by a single blinding point of light, dead ahead, burning bright enough to cast shadows through the hull. This is a confirmed optical phenomenon, predicted by Einstein and simulated in countless physics labs. Scientists call it the relativistic headlight effect. At high speed, the light from the entire sky in front of you gets funneled forward, compressed into a narrow cone. The faster you fly, the tighter the cone. The whole universe squeezes into a tiny spot at your nose. At 20% of light speed, the forward hemisphere of stars bunches into a circle, the size of a dinner plate held at arm's length. At half of light speed, a softball. At 90%, a marble. At 99, a pinhead of pure light blazing ahead of the ship, surrounded by pitch black in every other direction. Picture standing in a field at night. Stars cover the sky. Now run forward. The stars ahead appear to slide toward the point you're running toward. Now run at the speed of sound. The stars clump tighter around that point. Now run at the speed of light. Every star in the universe piles into a single dot, and behind you, the sky empties into perfect darkness. For the pilots, this creates a nightmare no flight simulator prepared them for. Navigation becomes impossible. The landmarks they trained on, the constellations they memorized, the reference stars they planned to steer by, have all collapsed into one indistinguishable smear of light. The compass of the galaxy has been erased. A team at the Massachusetts Institute of Technology ran the math in the 1990s. They found that a crew flying at 70% of light speed would see the entire Milky Way compressed into a glowing disk about 10 degrees wide. Everything else would be black. No way to tell which star was which. No way to aim. No way to steer. And the compressed light is not harmless. All that forward radiation, squeezed into a smaller patch of sky, grows more intense by the same factor. A dinner plate of sky dumps the energy of half a sky onto the forward hull. A marble of sky dumps the energy of an entire hemisphere. The front of the ship does not just see more light, it bakes in a searchlight aimed directly at it by the universe itself. Scientists at the University of Leicester simulated what a human eye would see. The results surprised them. Colours would shift. Some stars would brighten to blinding levels while others would blink out entirely. The view would look less like space and more like staring into a welder's arc through a pinhole. Windows cannot protect the crew. Cameras fail within minutes. The only survivable option is to fly blind, letting the ship's computers steer by inertial sensors and hope the course never drifts. Hope is a thin shield at 90% of light speed. The crew might accept the blindness. They might trust the computer. They might grit their teeth and ride the glare all the way to their destination. But there is another problem waiting, and this one does not care how good the autopilot is. The ship cannot carry enough fuel, not even close. The engineers gathered around the whiteboard in 1968 and did the math one more time. They kept hoping they were wrong. They were not. To push a single 1-ton probe to 10% of light speed using the best chemical rockets ever built, you would need a fuel tank larger than the planet Jupiter. To push the same probe to half of light speed, the tank grows to the size of the entire solar system. To reach 90%, the required fuel outweighs every gram of matter in existence. This is confirmed physics, written down by a Russian engineer named Konstantin Tsiolkovsky in 1903. The math is called the rocket equation, and it is as friendly to starships as a wolf is to a rabbit. The equation says the more fuel you carry, the more fuel you need to carry that fuel, which means more fuel to carry that fuel, in a spiral that runs off the edge of the page. Picture packing a car for a road trip. Add a gallon of gas. To carry that gallon, the car needs to burn a small sip of it. Fine. Now plan a trip so long that you need 100 gallons. The car needs a bigger tank. The bigger tank adds weight. The added weight burns more fuel. You add more gallons to cover that. The tank grows again. At some point, the car is all tank, no passengers, and still not enough fuel to finish the trip. That is the Starship problem. Every pound of propellant needs more propellant to lift it. The curve is not a slope, it is a cliff that rises straight up. Chemical rockets, the kind that launched every astronaut in history, max out around 10,000 miles per hour. Light speed is 67,000 times faster. No chemical mixture known to chemistry can close that gap. The energy locked inside hydrogen and oxygen is simply too small. Burning every ounce of fuel on Earth would not push a paperclip to 1% of light speed. Nuclear fission helps a little. A pound of uranium carries about 2 million times more energy than a pound of rocket fuel. Run the numbers again. A probe to Alpha Centauri in 200 years, instead of 75,000. An improvement, still not solution. Nuclear fusion helps more. A pound of hydrogen fused into helium releases about 4 times the energy of fission. A fusion rocket could reach 10% of light speed, crossing to the nearest star in 40 years, closer to possible, still at the edge of what humans can build. Antimatter is the theoretical dream. A pound of antimatter annihilating with a pound of normal matter releases every drop of energy locked inside both. A kind of pure conversion that Einstein's equation describes. A teaspoon of the stuff could power a city for a year. A fuel tank the size of a refrigerator could push a ship to half of light speed. There is one small problem. The entire human race has produced about 1/1000th of a gram of antimatter across all of history. At current prices, 1 gram would cost around $62 trillion, more than every government budget on Earth combined. Storing it safely requires magnetic traps colder than deep space. Making enough for a single voyage would take longer than human civilization has existed. A mathematician in California proposed building the ship around a bomb instead. A very specific kind of bomb, and the United States government actually tried it. The year was 1958. A team of physicists walked into a secret facility in San Diego and proposed the most terrifying spacecraft ever designed. They called it Project Orion. The plan was simple in the way only truly insane plans are simple. Build a ship the size of an aircraft carrier, strap a thick steel plate to the back, drop atomic bombs out of a chute, one every second, let them explode behind the plate, ride the shock waves to the stars. This was a real confirmed program funded by the United States Air Force and the early version of the National Aeronautics and Space Administration. The lead physicist was a man named Freeman Dyson, one of the sharpest minds of the 20th century. He believed Orion could reach Saturn in 2 years and Alpha Centauri within a single human lifetime. Picture a giant metal dinner plate, 1,000 feet wide, standing on end. Behind it, a stack of small nuclear bombs waits in a vertical magazine. Every second, one bomb drops through a hole at the base of the plate and detonates 50 yards behind it. The blast slams the plate forward with a force greater than every rocket ever built, combined, firing at once. Giant shock absorbers tall as office buildings squash and bounce to protect the crew. Another bomb drops, another shove. The ship climbs the explosions like a surfer rides a wave. The math checked out. Dyson and his team calculated that a properly designed Orion could reach 10% of light speed using about 300,000 hydrogen bombs. The ship itself would weigh 8 million tons. The crew could live in comfort, with gravity, gardens, and room for hundreds of people. Engineers actually tested a small version in the Nevada desert. A 5-foot prototype flew 50 feet into the air on a stack of ordinary chemical explosives, proving the shock plate could survive repeated blasts without shattering. Film reels of the test still exist. The little saucer leapt off the ground, hung in the air for a moment and thumped back down intact. Dyson called it the happiest moment of his career. Then the 1963 Partial Test Ban Treaty was signed, outlawing nuclear detonations in the atmosphere, in space and underwater. Orion died overnight. The plan to launch 300,000 nuclear warheads from American soil became, in a single pen stroke, illegal. Dyson himself later admitted relief. He'd begun to calculate how much radioactive fallout a ground launch would scatter across Earth. The numbers horrified him. A single launch would kill an estimated 1 to 10 people around the world, slowly, through cancer spread by drifting radiation. A fleet of Orion launches, he realized, would poison the biosphere itself. The design never left the drawing board after that. Engineers in the 1980s dusted off the blueprints a few times. Every review reached the same conclusion. The physics worked, the politics never would. Yet Orion proved something terrifying and beautiful at the same time. A starship was possible. Humans had already invented the engine. They simply could not bring themselves to use it. Across the Atlantic, a British team heard about Orion and decided to try something cleaner. No atomic bombs, no fallout, just pure fusion pellets, fired into a chamber faster than a machine gun. They called their ship Dedalus. 1973, London. A group of engineers from the British Interplanetary Society gathered in a small office above a print shop, drank too much tea and spent the next 5 years designing the first realistic starship ever put on paper. They called it Project Dedalus. The plan was to reach Barnard's star, a small red dwarf about 6 light-years from Earth, within 50 years. Not a generation ship, not a colony mission, a one-shot probe that would blaze past the target in a matter of hours, gathering data as it went. A flyby, like sending a postcard across interstellar space. The fuel choice was their boldest decision. Dedalus would run on fusion pellets. Tiny pea-sized spheres of deuterium and helium-3, ignited by electron beams inside a massive combustion chamber, exploding like miniature stars 250 times per second. Each blast would shove the ship forward. Over 4 years of steady firing, the engine would push the probe to 12% of light speed. Picture a cathedral-sized engine bell, glowing white from within, with thousands of tiny fusion flashes strobing inside it every second. Behind the bell, a stack of fuel tanks the size of skyscrapers. In front, a slim probe bristling with telescopes and radar dishes. The whole contraption would stand taller than the Empire State Building. The British team worked through every detail. They designed the electron beam ignition system. They calculated the heat dissipation. They drew the dust shield for the bow, a cloud of particles fired ahead of the ship to sweep the path clean. They even drew the little robotic landers that would drop off at the target star to examine any planets. Here was the catch. The fuel, helium-3, barely exists on Earth. Found only in trace amounts, embedded in lunar soil and the atmospheres of giant planets. To launch Dedalus, a fleet of scoop ships would need to spend 20 years hovering in the clouds of Jupiter, filtering out helium-3 by the ton, a mining operation bigger than any ever attempted by humanity, staged across 500 million miles just to fuel a single probe. The team acknowledged this. They did not flinch. Their report, published in 1978, simply listed Jupiter mining as a precondition and moved on. The Dedalus design ran 22 volumes. It included fault trees, failure modes, communication protocols, even psychological notes for the engineers back home who would wait 40 years for the first data transmission. The probe itself would never slow down. It would fly past Barnard's star at full speed, snapping photos and measurements for about 12 hours, then coast onward into empty space forever, a silent monument to a civilization that once tried. Engineers still reference the Dedalus study today. A modern version called Project Icarus, started in 2009, attempted to update the design with newer materials and better fusion models. 40 physicists and engineers across the world have been working on it. The timeline for construction remains the same, several centuries minimum. And Dedalus had one fatal flaw the British team understood perfectly. The probe could not stop. Whatever it found at Barnard's star, it would see for less than half a day before vanishing into the dark on the other side. A message thrown across 6 light-years of space, arriving as a single wave, and then silence. A second team in the United States decided a flyby was not good enough. They wanted a ship that could stop, orbit, and look around. 1987, the United States Naval Academy. A team of cadets and professors received an unusual assignment. Design a real, buildable starship using only technology that already existed or was within reasonable reach. No fantasy drives, no magic fuel. Engineering, not science fiction. The result was Project Longshot. The target was Alpha Centauri, our nearest stellar neighbour, 4.25 light-years away. The timeline was 100 years. The probe would not just fly past, it would slow down, enter orbit, and spend a decade photographing the star system and any planets it found. Then it would beam the images back to Earth, where children not yet born would watch them arrive. The design built on Project Dedalus but added a radical twist. Longshot would carry a small nuclear fission reactor, the size of a school bus, to generate electrical power during the voyage. The reactor would also power a laser that fired into the fuel pellets, triggering the fusion reactions that drove the ship forward. Inertial confinement fusion, lit by laser, not electron beams. A cleaner ignition, a more reliable engine. The ship would be about 350 feet long and weigh 400 tons at launch, not counting fuel. Another 300 tons of helium-3 pellets would ride in external tanks, consumed steadily over a 50-year acceleration phase, pushing the probe to 4% of light speed. Picture the probe cruising through the dark for half a century, its engine firing a pellet every few seconds, the fusion flash briefly lighting the hull. For 50 years, the ship falls upward through empty space, trailing a thin line of spent helium exhaust. Nobody alive on Earth when it launched would still be alive when it reached cruising speed. Then the real trick. Halfway through the voyage, the ship would flip around and fire its engine backward for another 50 years. A slow, patient break, burning through the rest of its fuel, peeling velocity off 100 kilometers per second at a time until the probe finally drifted into the Alpha Centauri system at a speed gentle enough to settle into orbit around one of its stars. The math required a fuel mass fraction of about 92%. For every 100 pounds of probe at launch, 92 pounds would be propellant, a staggering ratio, possible on paper, brutal in engineering practice. The cadets worked through every system. The radiators needed to shed fusion waste heat would span acres. The communication laser aimed back at Earth would need to hold its target across 4 light-years, a beam narrower than a human hair striking a coin on the far side of the galaxy. The computers would need to last a century without maintenance, a reliability record no human machine has ever approached. Longshot was accepted by the National Aeronautics and Space Administration as a formal feasibility study. The report still sits in the agency's technical archives, catalogued and available to any engineer curious enough to look. A real plan, signed, stamped, approved. It has never been built. The estimated cost in 1987 dollars ran into the trillions. The helium-3 mining problem from Dedalus remained unsolved. The construction would take decades, and no government has ever committed to a project that would not finish within an election cycle, let alone within a century. Longshot proved that a round-trip Starship was technically possible. It also proved something quieter and sadder. Possible and funded are two different things. One scientist believed there was a way around the fuel problem entirely. What if the ship did not need to carry fuel at all? What if it could scoop it up along the way? 1960. An American physicist named Robert Bussard was staring at a star chart when an idea hit him so hard he stood up from his desk. Space is full of hydrogen. Thin, sure, 1 atom per cubic inch in deep space. But a ship flying through that hydrogen at high speed could, in theory, scoop it up, compress it, and burn it in a fusion reactor. No fuel tanks, no launch mass problem. An engine that refueled itself from the universe as it moved. Bussard called his design the interstellar ramjet. Engineers today call it the Bussard ramscoop, and it haunted Starship dreams for half a century. The concept is simple. Imagine an enormous funnel at the front of the ship, wider than a city, made not of metal but of magnetic fields. As the ship flies forward, the funnel catches hydrogen atoms and channels them into a central combustion chamber. The hydrogen fuses into helium, releases energy, and that energy shoots out the back as thrust. The faster the ship goes, the more hydrogen it catches per second, the more power it generates. An engine that feeds itself and grows stronger the farther it travels. Bussard's math was beautiful. With a scoop about 60 miles wide, a ramjet ship could accelerate at a comfortable 1 gravity, the same pull you feel standing on Earth, forever. The crew could walk around normally. The ship could cross the galaxy in a human lifetime from the crew's perspective. Thanks to time dilation, it could reach the far side of Andromeda within 30 years of ship time, while millions of years passed on Earth. A ship that flies forever. A crew that never ages out of the mission. A fuel supply that never runs dry. Every science fiction writer in the world fell in love with the idea. Engineers spent decades refining it. Then the numbers started to turn. In 1989, a physicist named Thomas Heppenheimer at the American Institute of Aeronautics and Astronautics ran a careful simulation. The result crushed the dream. The hydrogen flowing into the scoop did not just provide fuel, it also provided drag. Every atom captured by the magnetic funnel had to be accelerated from a standstill to the ship's speed before it could fuse. That acceleration cost energy, a lot of energy, more than the fusion reaction produced. The ramjet, it turned out, was not a rocket. It was a break, a beautifully elegant galaxy-sized break. A follow-up study at the Princeton Plasma Physics Laboratory confirmed the verdict. To overcome the drag, the Scoop's fusion reactor would need to burn proton-proton fusion, the same reaction that powers stars. On Earth, physicists have never managed to ignite proton-proton fusion in a controlled way. It requires temperatures of 15 million degrees and pressures that only exist in the hearts of giant stars. A ship trying to run one would need a reactor denser than any object humans have ever built. Some engineers still work on modified ramjet designs. Newer versions use the scoop only to collect hydrogen, which is then stored and fused later at the ship's leisure. Others propose using the scoop as a pure drag brake at the destination, a free way to slow down without carrying extra fuel. The pure Bussard dream, though, is dead. And if you cannot scoop your fuel from the galaxy, there is one substance left that might work. A substance so dangerous that storing a single gram of it could level a city. Deep inside a laboratory at the European Organization for Nuclear Research, a team of physicists hovered around a magnetic trap the size of a refrigerator. Inside the trap, held in place by invisible fields, floated a single grain of antimatter. So rare, so valuable, so dangerous, that if the magnetic field failed for a millisecond, the grain would annihilate and release the energy of a hand grenade. That grain took the lab 3 years to produce. Antimatter is the mirror twin of ordinary matter. Every particle in your body has an antimatter counterpart, identical in every way except opposite in charge. When a particle of matter meets a particle of antimatter, both vanish in a flash of pure energy, described by Einstein's famous equation linking mass and energy. The conversion is total, no ashes, no waste heat, just a burst of gamma rays carrying every last drop of energy that was locked inside the particles. This makes antimatter the best fuel the universe offers. 1 gram of antimatter, annihilating with 1 gram of matter, releases as much energy as 43 kilotons of chemical explosive. Enough to level a small city. Also enough to push a starship to half of light speed with a fuel tank the size of a walk-in closet. A team at Pennsylvania State University, working with funding from the National Aeronautics and Space Administration, designed a real antimatter starship in the 1980s. They called it ICAN, short for Ion Compressed Antimatter Nuclear. The ship would carry about 140 micrograms of antimatter, use it to trigger small fusion reactions, and fly to Mars in 40 days. Not to another star yet, Mars. Getting the antimatter was the problem. Every particle accelerator on Earth, running every day for a full year, produces about 1/1000th of a gram of antimatter combined. At that rate, fueling the Penn State Mars mission would take 140 billion years, which is 10 times the age of the universe. The cost, calculated by the same team, came to about $62 trillion per gram. Not a typo, more than the annual economic output of the entire human species. A single microspeck of antimatter costs more than a small country. Storing the stuff is equally terrifying. Antimatter must never touch ordinary matter. Touching a wall, a floor, or a molecule of air makes it explode. The only safe container is a magnetic bottle, a region of vacuum surrounded by powerful magnets that hold the charged antiparticles in mid-air. A power failure, a computer glitch, a stray cosmic ray striking the magnet at the wrong moment, and the fuel tank detonates. a ship carrying a kilogram of antimatter would in effect be carrying the explosive yield of a 20 megaton thermonuclear warhead strapped to its belly. If anything ever went wrong during launch, the resulting blast would incinerate the launch site, the surrounding region, and leave a crater visible from orbit. Despite all this, several teams still dream of antimatter starships. A project called the Antimatter Drive Starship, studied at the Air Force Research Laboratory, calculated that 1/10 of a gram could push a small probe to 20% of light speed. A reachable goal if humans could ever make the stuff in bulk. The math says it would work. The economics say it never will. Not unless someone finds a cheap natural source of antimatter somewhere in the galaxy, and so far the galaxy seems to prefer the regular kind. Another team gave up on carrying fuel at all. They decided to leave it on Earth and send the push through a different medium. Light itself. 2016. A Russian billionaire named Yuri Milner stood at a podium in New York City beside the physicist Stephen Hawking and announced the most audacious starship plan of the 21st century. They called it Breakthrough Starshot. The idea broke every rule of traditional spaceflight. Forget the giant ship, forget the massive fuel tanks, forget carrying propellant at all. Instead, build 1,000 tiny probes, each the size of a postage stamp and weighing about as much as a paperclip. Attach each one to a lightweight sail, a few yards across, thinner than a soap bubble. Launch them all into low Earth orbit. Then, from the ground, fire a laser. A very specific laser. An array of 100 million tiny beams, synchronized and aimed at the sail from a desert in Chile or Nevada, combining into a single pulse powerful enough to produce about 100 gigawatts of output, more power than every commercial reactor on Earth, focused into a beam narrower than a football field, held steady on the target for exactly 10 minutes. In those 10 minutes, the laser would push the tiny sail to 20% of light speed. Then the beam would shut off. The probe would coast the rest of the way to Alpha Centauri. Travel time, about 20 years. Data return 4 more years after that. The first images of a planet around another star, arriving in human lifetimes for the first time in history. This is a real, funded, active program. Milner put $100 million of his own money into research. Hawking lent his name. A scientific board that includes Nobel laureates meets regularly to review progress. The physics has been checked by more than 24 universities. It works. On paper. The engineering, though, is a stack of problems taller than the laser array itself. The sail must be thinner than a human hair, yet strong enough to survive a force 5 billion times stronger than sunlight. Current materials flake apart at 1,000th of that pressure. The chip-sized probe must carry a camera, a radio transmitter, a power source, and shielding against cosmic dust, all weighing less than a quarter coin. The laser array must be built in a location with perfectly clear skies year-round and immune to atmospheric turbulence, which so far has defeated every telescope ever built, and the target, aiming the laser at a sail the size of a postcard, 400 miles above Earth, moving at orbital speed, holding the beam dead center for the full 10 minutes, requires tracking precision never achieved by any weapon or telescope. Any wobble, any drift, any cloud passing overhead, and the probe burns up instead of accelerating. The sail itself faces another problem. The laser does not push the sail evenly. If the beam wanders even a hair off center, the sail tilts. A tilted sail spins. A spinning sail catches the beam unevenly. Within milliseconds, the sail flips out of alignment and tumbles end over end, useless. Breakthrough. Starshot engineers have spent the past decade working on self-stabilizing sails, shapes that automatically recenter in the beam. Some designs look promising, none have been tested. The dream is simple. A civilization too heavy to fly sends a swarm of butterflies instead. 1,000 chips, each one a whisper of metal and plastic racing to the stars on beams of pure light. And then, partway through acceleration, the sail begins to heat. Not from friction, from the light itself. And the temperature climbs faster than anyone expected. The laser's been firing for 6 minutes. The sail is already glowing. Engineers at Breakthrough Starshot ran the simulations 100 times, hoping the numbers would change. They never did. A laser powerful enough to push a postage stamp probe to 20% of light speed also dumps so much energy into the sail material that the sail itself begins to cook. Here is the math, stripped down. 100 gigawatt laser pointed at a sail about 13 feet across delivers about 60 megawatts of power per square foot. That is roughly 60,000 times stronger than a summer day on a tropical beach. Most of the light bounces off, but even the tiniest absorption, a fraction of 1%, leaves the sail heated to glowing orange within seconds. A little more and the sail reaches the melting point of aluminum. A little more still and it vaporizes into a puff of metal dust that scatters in the laser beam. Picture holding a sheet of aluminum foil in front of a blowtorch. Fine for a second. The foil reflects the flame. Hold it for 10 seconds and the foil begins to crinkle. Hold it for 30 and it curls up, glows and falls apart. The laser sail faces the same fate, except the blowtorch is 1,000,000 times hotter, and the foil must survive the full 10-minute blast without a single warp, tear or bubble. A team at the University of California, Santa Barbara has spent 6 years hunting for a material that can take it. They have tried aluminum, beryllium, carbon nanotubes, silicon dioxide. Everyone failed in testing. Either the material absorbed too much heat, or it cracked under the pressure, or it tore at the edges where the sail attached to the chip. The current favourite is a layered stack of silicon nitride and molybdenum disulfide, exotic crystals grown one atom at a time in specialised laboratories. Early tests suggest this combination might survive the blast, if the sail is made reflective enough that it bounces back 99.995% of the incoming light. Anything less, and the remaining absorbed energy cooks it anyway. Manufacturing a sail that reflective, at the size and thinness required, has never been done. The record so far is about 99.6% reflectivity, which is close, but at this scale, close is the difference between success and a cloud of vapour. Then comes the shape problem. A flat sail catches the beam unevenly, leading to tumble as we covered. Engineers want to curve the sail into a shallow bowl, a shape that self-stabilizes in the beam. A curved sail, though, stretches differently across its surface. The centre heats faster than the edges heat faster than the rim. Thermal stress builds up. Microscopic cracks begin to spread. A separate team at Harvard University suggested spinning the sail during the boost, like a frisbee, to even out the heating. The idea works in simulations. In practice, a spinning sail at 20% of light speed faces every interstellar dust grain edge-on, making the already deadly dust problem even worse. And if the sail does survive the boost, a final cruelty waits at the other end of the journey. The probe arrives at Alpha Centauri at 20% of light speed, with no engine, no fuel, and no brakes. It cannot stop. It blazes past its target in less than an hour, snapping photos as it goes, then vanishes into deep space forever. A 24-year voyage, a 50-minute visit. And still, the camera must not tumble, not even once, while the universe tries to throw it off course with every pebble in its path. The ship has been travelling for 6 years. The navigator runs the morning check. The course reads dead on target. Alpha Centauri 4 light-years ahead, right where the chart shows it. Perfect. Then the physicist on board points at a different number on the screen and says 3 quiet words. We missed it. At relativistic speed, navigation is a nightmare no ordinary pilot has ever faced. A ship cruising at 20% of light speed covers about 40,000 miles every second. A course correction of 1 single degree, applied even a year into the voyage, shifts the arrival point by hundreds of millions of miles. An error of 1/10 of a degree misses the destination star by a distance greater than the orbit of Pluto. A 1/100th of a degree error, about the width of a human hair held at arm's length, still throws the arrival off by a distance farther than Earth is from Mars. For a probe flying at 87,000 miles per second, with no fuel to correct after the boost, that miss cannot be recovered. The probe flies past its target in empty space, cameras aimed at nothing, and disappears. Picture an archer in New York City shooting an arrow at a soup can in Los Angeles. The arrow travels for a week. A breeze along the way pushes it a fraction of an inch off course. By the time it arrives, it misses the can by several states. That is the navigation problem for a relativistic starship, except the distances are 1 trillion times larger, and the soup can is orbiting around a moving star. The stars themselves do not sit still. Alpha Centauri is moving through space at about 15 miles per second relative to Earth. In the 20 years it takes breakthrough Starshot probes to arrive, the target will have shifted by more than 9 billion miles. The navigator must aim not at where the star is, but at where the star will be, down to the second, based on measurements taken 2 decades before. And even those measurements carry uncertainty. The best telescopes on Earth can pin down the position of Alpha Centauri to within a few million miles, a precision that sounds incredible, right up until you try to hit a small planet around the star with a probe moving at 1/5 the speed of light. A team at the Jet Propulsion Laboratory ran the error budgets for a relativistic flyby mission. They listed 47 separate sources of navigation uncertainty: launch misalignment, laser beam wobble, sail tilt, dust impacts during cruise, gravitational nudges from passing stars and rogue planets the probe cannot detect. Each error on its own sounds tiny. Combined, they spread the probe's final position over a volume of space larger than the entire inner system it was trying to reach. The only known solution is onboard course correction, thrusters, steering jets, the ability to nudge the probe a hair in the right direction mid-flight. At a postage stamp scale, with a mass budget measured in grams, there is no room for thrusters. The chip has room for a camera, a radio, and a battery, nothing else. Larger ships could carry steering engines, but at relativistic speed, firing an engine sideways is its own horror. A thrust strong enough to correct the course would generate forces the crew cannot survive. A thrust gentle enough to be safe would correct the path by less than the width of the original error. So even if the ship survives the dust, the radiation, the blue shift, the fuel paradox, and the sail melting, it might arrive to find nothing waiting but empty darkness, the target star a faint blur off to one side, forever unreachable, and long before the course error even becomes visible, the ship has gone silent. Because the radio signals to Earth stopped reaching home years ago. The last message from Earth arrived 6 months ago. The crew does not know it is the last message. They will find out 20 years from now, when the return signal they're expecting never comes. Radio waves, the same waves that carry phone calls, television, and every message ever sent between humans, travel at exactly the speed of light. No faster, ever. This is confirmed by every experiment since the late 1800s. At terrestrial distances, the delay is too small to notice. A call from New York to Tokyo takes about 1/25th of a second, practically instant. At interstellar distances, the delay becomes a wall. A message from Alpha Centauri to Earth takes 4 years and 3 months to arrive. A reply takes another 4 years and 3 months to return. A simple question and answer consumes nearly 9 years of waiting. A ship 2 light years out and moving away at 20% of light speed faces an even crueler delay. By the time the message reaches home, the ship has flown another few months deeper into the void. The reply racing back chases a target that keeps fleeing. The gap grows every day. Scientists at the Deep Space Network, run by the National Aeronautics and Space Administration, call this the speed of light horizon. For any spacecraft farther than a few light hours, real-time conversation becomes impossible. Ground control cannot advise on emergencies. Mission planners cannot respond to new discoveries. The crew is alone with decisions that used to require a committee on Earth. Picture a firefighter calling headquarters to ask which door to break down, then waiting 9 years for the answer. By the time the response arrives, the building has burned down, been rebuilt, and caught fire again. The technical problem gets worse. Radio signals weaken with distance, following a simple law from classical physics. Double the distance, cut the signal strength to 1/4, triple the distance 1/9. At 4 light years, a radio signal from a starship reaches Earth about 20 trillion times weaker than it started. To catch that whisper, Earth would need receiving antennas larger than any built so far. The current record holder, the Green Bank Telescope in West Virginia, spans about 300 feet across. A team at the Search for Extraterrestrial Intelligence Institute calculated the size of antenna required to hear a starship beaming from Alpha Centauri with reasonable fidelity. Their answer: about a mile wide. On Earth or in space, no nation has ever committed to building one. Breakthrough Starshot plans to sidestep this by using lasers for communication instead of radio. A laser from the chip, aimed back at Earth, can carry a signal thousands of times stronger per unit of power than a radio beam. The catch is aim. As we covered earlier, steering a laser beam across 4 light years requires a pointing accuracy so extreme that no current technology can match it. The beam arrives, but it may not arrive at the intended receiver. It may drift past Earth by a mile or 100 miles or the width of the planet, and the signals that do arrive come stretched out by time dilation and Doppler shift. A 1-second message sent from a ship moving at 20% of light speed arrives at Earth stretched into 1¼ seconds, every syllable slowed, every pitch lowered. The engineers on Earth must decode not just a weak signal, but a distorted one. The crew, meanwhile, hears nothing back. No advice, no comfort, no news of their families. For years on end, the ship drifts through a silence so deep that some crew members stop checking the radio at all. The isolation would be bearable, maybe, if the crew was healthy. They are not. The pilot's fingers will not close around the handrail. Her bones have lost 15% of their mass. Her muscles have shrunk to the width of a child's. Her heart, starved of the steady pull of gravity, beats slower and weaker. And the ship has only been in flight for 18 months. The human body is a creature of Earth. Every bone, every muscle, every vein is designed for the pull of one gravity, the steady tug that has shaped life on our planet for billions of years. Take that pull away, and the body begins to unravel. Astronauts on the International Space Station have provided decades of confirmed data. In 6 months of weightlessness, a typical astronaut loses about 1 to 2% of bone density per month. Muscles shrink by up to 20%. Fluids rise toward the head, swelling faces and flattening eyeballs. Vision blurs. Some astronauts return to Earth with eyesight permanently damaged. A man named Scott Kelly spent a year aboard the station and came back 2 inches taller with altered gene expression in thousands of his cells and a body that took months to relearn how to walk. That was 1 year, in low Earth orbit. With regular exercise, medical monitoring and constant supply shipments, a Starship crew would face years or decades in microgravity, with no supply runs, no new medicine, no return ticket. By year 5, their skeletons would creak like old wood. By year 10, a fall against a bulkhead could shatter a hip. By year 20, the crew that launched as elite pilots would arrive at the destination as frail, shrunken shadows of themselves, barely able to stand even in reduced gravity. The obvious fix is artificial gravity. Spin the ship, let centrifugal force press the crew outward against the walls. The walls become the floor. The body feels weight again. Bones stay strong. Muscles stay firm. This works. Scientists have tested it on small scales aboard research aircraft. A spinning ship does produce gravity-like force. The problem is scale. To generate one gravity without making the crew dizzy, the spinning section must be at least 300 feet across. A mile across would be more comfortable. That's a spacecraft the size of a small city. Every foot of extra spin radius adds weight. Every pound of extra weight demands more fuel. More fuel demands more engine. More engine demands more fuel still. The Starship grows until it becomes too massive to launch. Then comes the acceleration problem. To reach relativistic speed in a human lifetime, the ship must accelerate at about 1 gravity steadily for years. The crew would feel the push as a downward force, pressing them into their seats as if gravity never left. That works fine. The issue arrives during the mid-flight flip, when the ship turns around to begin braking. For a brief period, there is no acceleration and no spin. The crew floats. Their bones begin to thin again. Then the braking begins, pressing them from the other direction. A team at the Massachusetts Institute of Technology modelled what would happen to a crew during a relativistic voyage. The results were grim. Even with a spinning ship and constant acceleration, the variation in forces during maneuvers would cause chronic spinal injuries, nerve damage, and a condition they nicknamed corridor syndrome. A disorientation so severe that crew members could no longer tell up from down. And these are the crew that stays awake. The ones who try to sleep through the journey face a different kind of horror. The freezer bay hums with a low blue light. Inside the first pod, a woman lies perfectly still. Her skin is white, her lips are blue. Her heart has not beaten in 11 months. According to the ship's plan, she will wake up in 40 years, step out of her pod, and help land the ship around another star. According to current medical science, she is never waking up again. The dream is old. Cryogenic sleep, freeze the crew, skip the lonely decades, thaw them at the destination. Science fiction has used the idea for more than a century. Real researchers have worked on it for almost as long. The math is compelling. A frozen body needs no food, no water, no oxygen, no exercise. It does not age. It does not go mad in the silence. A cryogenic crew solves the psychology problem, the supply problem, and the time dilation problem all at once. The biology refuses to cooperate. Human cells are mostly water. When water freezes, it forms sharp crystals that grow outward in spiky needles. Inside a living cell, those crystals tear through membranes, rupture tiny organs called organelles, and shred the delicate machinery that keeps the cell alive. A frozen cell is a dead cell. Thawing does not bring it back. Scientists have tried for decades to get around this. The main trick is called vitrification, where the body is pumped full of chemicals called cryoprotectants that turn the water inside cells into glass instead of ice. Glass forms no crystals. A glassified cell, in theory, could be revived. In practice, the chemicals themselves are toxic. Every cryoprotectant that prevents ice crystal damage kills cells through a different pathway, usually by poisoning the protein machinery. Teams at laboratories like 21st Century Medicine in California have successfully vitrified individual organs. A rabbit kidney was frozen, glassified, warmed and transplanted back into a living rabbit in 2024. The rabbit survived. A whole human body is a different beast. Organs freeze at different rates. A skin layer may glassify while a deep muscle is still liquid. The body cracks, blood vessels shatter. The brain, the most delicate organ, suffers the most. Brain tissue frozen with current methods shows extensive fracture damage, the kind that cannot be repaired by any current medicine. Picture trying to freeze a water balloon. The outside becomes ice. The inside remains liquid. The expanding ice cracks the rubber. Now try that with a balloon made of 10,000 interlocking parts, each one essential for life, each one freezing at a different temperature. One crack anywhere and the balloon is dead. Even if the freezing worked, the thawing is worse. Warming a body back up must happen evenly, or the outer layers cook while the inner core is still frozen. No current technology can warm a human body uniformly. Microwave methods have been tried, causing spot heating and internal burns. Warm liquid baths are too slow, allowing ice to reform during the thaw. A Starship crew frozen for a 40-year voyage faces a problem no laboratory has yet solved. Launch them with current technology, and they arrive as cryogenic mummies, preserved but never recoverable. The destination receives a ship full of statues. Some researchers argue the problem is only an engineering hurdle. Give it another 50 years, they say, and vitrification will be reversible. Others, including many cryobiologists, believe the barrier is fundamental. Biological complexity, they argue, cannot survive the phase change of water. The physics simply does not allow it. Until someone proves one side wrong, the freezer bays stay empty, which leaves only one option. A ship where the crew stays awake, has children, and watches them grow old before the journey ends. The young boy presses his nose against the forward window. His mother stands behind him. His grandmother is in the galley. His great-grandmother is asleep in her quarters. Outside, the stars have barely moved in 80 years. Nobody on board has ever walked on a planet. Nobody will. Their entire universe is 11 decks, 6 gardens, 3 recreation halls, and a crew of 400 people who are also their entire species. This is the generation ship, the oldest realistic plan for reaching another star. Forget light speed, forget cryogenic sleep. Build a vessel large enough to house a self-sustaining population, accelerate it to a few % of light speed, and let it cruise for centuries. The original crew dies. Their children are born on board. Their grandchildren grow up knowing only the ship. Somewhere around the 10th generation, the descendants arrive at the destination, step onto a new world, and begin human history over again. A team at the French Research Institute called the Interstellar Generation Ship Initiative ran the numbers in 2018. To maintain a genetically healthy population over 500 years, a starship needs a minimum of about 98 unrelated adults at launch. To be safe against disease, accident, and random bad luck, the real number should be closer to 500. For long-term social stability, more like a few thousand. Each person needs food, water, air, medical care, education, and living space. The ship must be the size of a small city. Picture a metal cylinder 20 miles long and 5 miles wide, spinning slowly for artificial gravity, farms on the inside curve, schools and hospitals near the centre, forests along the axis where the gravity is weakest. Generations of humans living their entire lives inside, never seeing a horizon, never feeling rain, never looking up at a real sky. The engineering is massive but imaginable. The social science is the part that keeps researchers awake. A study led by a team at Portland State University in 2020 simulated 5 centuries of multi-generational starship society. The findings were unsettling. By the 3rd generation, knowledge from Earth began to fade into myth. By the 5th, the mission itself was questioned. Why were their ancestors so desperate to reach a distant star, the young people asked. Why should they spend their lives preparing for a landing they would never see? The researchers found that every simulated generation produced at least one serious revolt, demanding the ship stop or turn around. Real history agrees with the simulation. Isolated human communities on Earth have splintered, collapsed, or gone mad within a few generations. A Russian trapping family called the Likovs lived alone in the Siberian wilderness for 40 years, cut off from the outside world. When researchers found them, the children born in isolation could not imagine a city. They thought the world was a few acres of pine forest. Scale that to centuries, multiply by a spaceship, and the psychological strain becomes something no modern society has ever tested. And the genetics. 98 founders sounds like a lot, but inbreeding accumulates over generations. Every child born on board slightly narrows the gene pool. By generation 10, without careful management, the crew shows the same medical patterns as the royal families of medieval Europe. Haemophilia, heart defects, shortened lifespans. Some designs propose a frozen embryo bank, thousands of genetic samples stored as backups, thawed and implanted whenever the gene pool needs refreshing. This works on paper. In practice, it requires the shipboard culture, centuries removed from Earth, to accept strange children from a vanished civilization as equal members of their society. History suggests this is a lot to ask, and the ship itself is not safe. A single rogue atom striking at the wrong angle can cook the crew in their sleep. The alarm is a quiet chirp, almost gentle. The engineer glances at the panel. Radiation in the habitat ring has spiked above the safe limit. The crew has 6 hours before the damage becomes permanent. She goes to wake the captain, then remembers that the captain died of leukemia 2 years ago and nobody has fixed the shielding. Radiation is the slow killer of every long-duration space mission. Astronauts on the International Space Station absorb about 10 times the dose of a person on the ground. The field surrounding our planet blocks most of the worst radiation, a magnetic bubble called the magnetosphere that deflects cosmic rays before they reach the surface. Beyond that bubble, the rays come in unfiltered. Every piece of shielding ever designed struggles to stop them. 3 types of radiation threaten a starship crew. First, solar particles, streaming out of our closest star in gusts and storms. easy enough to block with a few inches of aluminum, the same stuff rockets are made from. Second, cosmic rays, atomic nuclei fired through the galaxy by supernova explosions travelling at close to the speed of light. These are the hard ones. A single cosmic ray striking a ship's hull smashes through the aluminum, strips electrons off atoms as it passes, showers secondary radiation through the interior, and finally slams into a crew member's body where it damages cells along its entire path. Multiple feet of solid shielding are needed to stop the worst of them. Water tanks, lead sheets, concrete walls. Every inch adds mass. Third, relativistic radiation. This is the new one, the one that only appears at starship speeds. As we covered earlier, the hydrogen atoms in interstellar space strike the forward hull with the energy of gamma rays when the ship is cruising fast enough. No normal shield material survives that kind of continuous bombardment. Aluminum turns brittle in weeks. Lead absorbs the rays but heats up to molten temperatures. Water shields boil away. Scientists at the European Space Agency proposed a clever workaround in 2019. A magnetic shield. A bubble of powerful magnetic fields projected around the ship, bending charged particles away before they strike the hull. The same trick our planet uses, shrunk down to spacecraft scale. The problem is energy. Our planet's magnetic field is generated by thousands of miles of molten metal churning in the core. A spacecraft would need a superconducting magnet coil hundreds of feet wide, cooled to near absolute zero, powered by a reactor so massive it doubles the weight of the ship. Early designs work at low speeds, deflecting solar particles during a trip to Mars. At relativistic speed, the required field strength climbs beyond any material that can carry the electrical current without melting. A team at the Plasma Science and Fusion Center ran the math. For a ship at 20% of light speed, the magnetic shield would need to produce a field roughly 100 times stronger than the strongest ever tested in a laboratory. Possible in principle, not with any technology humans have today. Some designs try stacking defences, an outer layer of ice meters thick to absorb high-energy strikes, an inner layer of lead for gamma rays, magnetic coils for charged particles, a fourth layer of water tanks doubling as drinking supply and final radiation buffer. The combined shield could work. It also weighs more than the rest of the ship. Fuel costs spiral again. Meanwhile, the ship itself is playing a cruel trick. Every time the engines fire, every mile per hour of added speed, something strange is happening to the mass of the vessel, something Einstein warned about in 1905, and the engineers are only now appreciating how bad it gets. The engine has been burning for 3 years straight. The ship should be going faster. The instruments say it is, but the acceleration, the feeling of being pressed back into the seat, has weakened. The engineers check the fuel flow, normal. They check the thrust, normal. They check the mass of the ship, the mass is climbing. This is confirmed physics, written by Einstein in 1905 and tested in particle accelerators countless times. As any object speeds up, its mass increases. At walking pace, the effect is too small to notice. At orbital speed, a few extra ounces on a ship that weighs tons. At relativistic speed, the gain becomes crushing. At half of light speed, a ship weighs about 15% more than it did at rest. At 90%, more than double. At 99%, 7 times heavier. At 99.9, more than 20 times heavier. At 99.99, more than 70. The closer you push to the speed of light, the more mass the ship carries, and the harder it becomes to push any faster. This is not a metaphor. The added mass is real. A scale on board the ship would show a crew member growing heavier as the ship accelerates. A cup of coffee sitting on the table presses harder against the saucer as the ship approaches light speed. The ship itself creaks under its own rising weight. Picture pushing a car uphill. The hill is steep at first. You lean into it. The car rolls slowly upward. Then the hill gets steeper, harder to push, then steeper still. You strain every muscle. The car still moves but barely. Then the hill turns vertical. The car weighs 10 times what it used to. You cannot budge it no matter how hard you push. That is the relativistic wall. The closer you get to light speed, the steeper the hill becomes. A ship that was easy to accelerate at 10% of light speed requires twice the energy to accelerate the same amount at 90, 10 times the energy at 99, 100 times at 99.9. The numbers climb toward infinity as the speed approaches the ultimate limit, and this is why no ship can ever reach light speed. Not because engineers lack imagination, because physics itself forbids it. To reach light speed, the ship would need infinite mass, requiring infinite energy, which no universe contains. A team at the Lawrence Berkeley National Laboratory made a subtle point in a 2012 paper. The mass gain is not just an abstract number. It affects every system on the ship. The engines must push harder. The navigation computers must account for heavier control surfaces. The crew feels heavier under acceleration. A workout that was difficult at launch becomes impossible at high cruise. A small impact that would scratch the hull at low speed becomes a catastrophic strike at high speed because the ship itself is harder to shove aside when the debris hits. The silver lining is that the ship grows heavier symmetrically. The extra mass helps punch through dust clouds more robustly. A heavier hull takes impacts with less displacement. The extra inertia keeps the ship steady on course, less likely to be deflected by stray gravitational nudges from passing stars. The dark lining is much larger. At the halfway point of any relativistic voyage, the engines must flip and begin to brake. The same mass that made acceleration so costly now fights the deceleration just as hard. Every ounce of extra weight at top speed must be peeled back off at equal cost before the ship can stop. Which is where Starship design meets its oldest and cruelest truth. Stopping is harder than starting. The ship is halfway to its destination. The crew celebrates with a small ceremony in the observation deck. Then the engineers begin the most dangerous maneuver of the entire voyage. The ship must flip. For years, the engines have fired forward, pushing the crew into their seats. Now the thrusters on the sides rotate the entire vessel end over end. For a few minutes, the ship spins slowly in empty space. Then the engines, now pointed at the destination, ignite again. The push reverses direction. The crew feels the force swing through 90 degrees, then 180, then slam them in the opposite direction. Braking has begun. And the fuel counter is already telling them something grim. The return trip, the slowing, the gentle arrival at Alpha Centauri requires every bit as much energy as the launch did. The fuel tanks that were half full at the midpoint will be empty when the ship finally drifts into orbit. This is the rocket equation biting a second time. To stop a ship moving at 10% of light speed requires the same energy as it took to accelerate it to that speed in the first place. Symmetrical, merciless. The galaxy does not offer any free deceleration. If you want to arrive, not just fly past, you must pack fuel for both legs of the journey. The consequences cascade through the design. A ship that wants to reach Alpha Centauri in 50 years, stop and orbit, needs about 4 times more fuel than a ship that just plans a flyby. A ship that wants to come back to Earth afterward needs 16 times more fuel. The rocket equation squares at every stage, eating the mass budget alive. Project Longshot, the United States Naval Academy design, acknowledged this directly. Half the fuel, they wrote, would be spent in the first 50 years of acceleration. The other half would be spent in the second 50 years of braking. The ship would arrive at Alpha Centauri with its tanks completely dry, its engine dead, and no way to leave. Breakthrough Starshot sidesteps the problem by not stopping at all. The postage stamp probes fly past their target at 20% of light speed, snap photos for a few hours, and continue into deep space forever. A one-shot view, a postcard from the edge. Larger, crude ships cannot afford that luxury. A flyby of another star is scientifically interesting but practically useless. You cannot study a planet in detail while blazing past it in less than an hour. You cannot land on a world you're moving too fast to orbit. You cannot establish a colony if your ship cannot stop. Engineers have proposed creative workarounds, a magnetic brake at the destination, using the target star's own solar wind to drag against a giant sail. A light sail reversed at arrival, catching the destination star's rays to slow down over months. A gravitational slingshot around a massive planet, bleeding off velocity through a carefully planned pass. Every solution adds complexity. Every added complexity adds mass. Every added mass adds fuel. The spiral never ends. The most honest assessment came from a physicist named Claudio Marcone at the International Academy of Astronautics. In a 2009 paper, he calculated that any crude interstellar mission with braking and return capability would require fuel mass on the order of 10,000 times the payload. For a 1-ton probe, 10,000 tons of fuel. For a 100-ton ship, 1,000,000 tons. For a generation ship holding 1,000 colonists, a fuel load greater than the mass of a small moon. A government in the United States once tried to fund real research into how to escape these limits. They shut the program down in silence. 1996. A small office opened inside the National Aeronautics and Space Administration Glenn Research Center in Ohio. The name on the door read Breakthrough Propulsion Physics. The mission was to investigate propulsion concepts that could bypass the rocket equation entirely. Faster-than-light drives, reactionless thrusters, exotic physics that might let a ship move without throwing fuel behind it. The budget was small, about $1 million over its lifetime. The staff was tiny, the ambitions were enormous. A man named Mark Millis led the program. A soft-spoken engineer who had spent years collecting unconventional propulsion papers in a filing cabinet at home, waiting for the day his employer would let him study them formally. When the program opened, Millis invited physicists from around the world to submit proposals. The inbox filled within weeks. The submissions range from elegant to wild. Some researchers proposed using quantum vacuum fluctuations, the tiny bursts of energy that flicker in and out of empty space, as a source of thrust. Others suggested modified versions of general relativity, where space itself could be stretched and compressed to carry a ship forward without the ship having to move. A few explored whether inertia, the property that makes objects resist being pushed, might be adjustable through exotic fields. Most of the proposals did not work, that was expected. The program's goal was to identify which ideas had the best chance of surviving rigorous testing, and to fund small experiments to check the math. One of the most famous tests involved a device called the EM drive, a metal cone inside which microwaves were bounced around. The inventor claimed the device produced thrust without any propellant, apparently breaking the conservation of momentum, a rule that has held unbroken since the 17th century. Early measurements at low precision seemed to show a tiny thrust. Follow-up measurements at higher precision showed the thrust was probably an artifact of testing conditions. The effect, if it was real, was 1,000 times smaller than the measurement noise. Another test involved the Mach effect thruster, proposed by a physicist named James Woodward at California State University, Fullerton. Woodward argued that a vibrating capacitor, tuned to a certain frequency, could produce thrust by interacting with distant matter in the universe through a subtle gravitational effect. His experiments have shown microscopic thrust signals for more than 2 decades. Critics say the signals are thermal noise. Supporters say the signal grows with each improved apparatus. The Breakthrough Propulsion Physics program ran for 6 years. It published peer-reviewed papers. It funded dozens of small experiments. It found no working prototype for any exotic drive. In 2002, the program quietly closed. The official explanation was budget reallocation. Unofficial accounts described deeper tensions. The program was generating attention, some of it unflattering, about the agency sponsoring what critics called fringe physics. The filing cabinets were emptied. The website went dark. The principal investigators moved on to other projects. Millis founded a non-profit to continue the work, called the Tau Zero Foundation, which still operates today. A handful of retired physicists and engineers meet online, publish papers, and wait for the day when another government will dare to fund the question again. The program's final report contained a single sentence that haunted the community afterward. Not one of the propulsion concepts examined during the 6 years of the program could be conclusively ruled out. The door to faster-than-light travel remained cracked open. One equation in particular keeps the door from closing, written by a physicist in Mexico, and the math is beautiful and impossible. 1994. A young Mexican physicist named Miguel Alcubierre sat in a quiet office at the University of Wales. He'd been reading science fiction for most of his life. He'd been reading relativity for half of it. A thought occurred to him that day. Maybe both could be true. Einstein's theory forbids any object from moving through space faster than light. That is settled physics. What Einstein's theory does not forbid is space itself moving faster than light. Space can stretch. Space can compress. Space can warp in ways that have been observed directly. The expansion of our universe, visible in the light of distant galaxies, is itself a kind of superluminal motion. Space is moving away from us faster than light can cross it, at the farthest edges of observation. Alcubierre wondered if that same trick could be harnessed at smaller scales. Could a ship ride a bubble of warped space, the way a surfer rides a wave without ever moving through the space around it? The ship itself would sit motionless inside the bubble. The bubble would stretch the space behind the ship and compress the space ahead. The ship would arrive at its destination in hours, while the universe outside the bubble watched light take years to catch up. He sat down and wrote the equations. They worked. The paper, titled The Warp Drive, was published in 1994. It described a specific mathematical solution to Einstein's equations that produced exactly the effect Alcubierre had imagined. A starship could be enclosed in a bubble of stretched space, the fabric of the universe itself flowing past the ship like a river carrying a boat, no relative motion between ship and bubble, faster than light travel without breaking relativity. The physics community was stunned. Nobody had thought to check whether Einstein's equations allowed such a thing. They did. The math was clean, elegant, and apparently perfect. Then Alcubierre added the caveat that has frustrated physicists ever since. To build the bubble, a ship would need a ring of negative energy, an exotic substance with properties opposite to normal matter. Where normal mass curves space one way, negative mass would curve it the other way, allowing the warping to happen. Negative energy, as far as anyone knew in 1994, did not exist. It was a mathematical placeholder, not a real substance humans could manufacture. The amount required was also a nightmare. Alcubierre's first calculations suggested that warping a spaceship-sized bubble would require negative energy, equivalent to the mass of the planet Jupiter, converted into pure exotic matter and held stable around the ship. A resource far beyond any civilization's ability to produce. Later work reduced the requirement. In 2000, a physicist named Chris van den Broek proposed a modified bubble that shrunk the interior while keeping the exterior small, reducing the energy requirement by a factor of billions. By the 2010s, researchers at the Johnson Space Center, including a scientist named Harold White, were calculating even more optimistic versions. A ring of negative energy the size of a wedding band, they suggested, might produce a usable warp. Every step forward, though, collided with the same wall. Negative energy is still a ghost, never produced in usable quantities, never even proven to exist at the density required. One experiment in a laboratory gave a hint that the ghost might be real, a hint so strange, so subtle, that most scientists still argue about what it means. It involves two flat plates of metal suspended in a vacuum, pressing toward each other with a force that should not be there. 1948. A Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory in the Netherlands when he noticed something strange in his calculations. Take two flat metal plates, polish them smooth, place them parallel to each other in a perfect vacuum separated by a tiny gap about the width of a human hair. According to classical physics, the plates should sit there, motionless, with no force between them. Casimir's equation said otherwise. The plates he calculated would press toward each other with a small, measurable force, not because of gravity, not because of magnetism, not because of any known interaction between metals. The force came from the vacuum itself. Empty space, according to quantum mechanics, is not truly empty. It seethes with tiny, fleeting pairs of particles that flicker into existence for a billionth of a second and then vanish back into nothing. Virtual particles, physicists call them, countless trillions of them, appearing and disappearing everywhere in the universe at every moment. Each pair carries a small amount of energy. Together they give empty space a faint background energy that fills every cubic inch of the cosmos. When you place two metal plates very close together, Casimir realized, you change the rules. Inside the gap, only certain wavelengths of virtual particles can fit. The plates act like a filter, blocking longer wavelengths. Outside the plates, all wavelengths exist. The pressure of virtual particles outside is slightly higher than the pressure inside. The plates get squeezed together. This prediction sat in physics journals for nearly 50 years as a theoretical curiosity. Then, in 1997, a physicist at the University of Washington named Steve Lamoureux built the experiment. Two plates, 1 inch across, polished to atomic smoothness, suspended in a vacuum chamber. He measured the force. It was exactly what Casimir predicted. The Casimir effect is real. It has been confirmed by a dozen independent laboratories since. The force is tiny, roughly the weight of a few red blood cells on a plate the size of a postage stamp, but it is unmistakably there. Here is why Starship engineers care. The region between the Casimir plates has less energy than empty space. It is, by the strictest definition physics allows, a region of negative energy. Not negative in the sense of being owed like a bank account. Negative in the sense of containing less energy than the vacuum around it. A mathematical minus sign in the equation for energy density. This is the same kind of negative energy that Alcubierre's warp drive requires. The Casimir effect in principle proves that negative energy can exist. A physicist named Lawrence Ford at Tufts University calculated how much negative energy can be produced this way. His answer was discouraging. The effect is real, but the amount of negative energy is minuscule. Building up enough to warp a spaceship bubble would require Casimir plates stacked by the trillions, covering a surface area larger than the orbit of our planet, held stable against the tiny forces pulling them together. Still, the door remained open. The Casimir effect said, in no uncertain terms, that the universe allows negative energy to exist. Whether in usable quantities, for something as grand as a warp drive, remains an unsolved problem. Meanwhile, another corner of Einstein's math suggested a different kind of shortcut. A tunnel through space itself. A bridge between two distant points that could be crossed in an instant. The only problem is that the bridge collapses on anything that tries to cross it. 1935. Albert Einstein was sitting at his desk at the Institute for Advanced Study in New Jersey. His assistant, Nathan Rosen, was working through a puzzling solution to the equations of general relativity. Together they found something impossible. The mathematics of a black hole, they realized, included a second mirror image solution. Not just an object that pulls matter in forever, but an object that connects to another place. A bridge. A tunnel. If you entered one black hole, the equation suggested, you would emerge from a corresponding object somewhere else in the universe. They called it an Einstein-Rosen bridge. Later scientists renamed it the Wormhole. The idea became the dream of interstellar travel. Forget speed of light. Forget fuel equations. A wormhole could connect 2 points separated by 1,000 light years, allowing a ship to cross the distance in a single step. Enter here. Exit there. The universe. Shortcut. Physicist Kip Thorne at the California Institute of Technology became the most famous advocate of the idea. In 1988, working with colleagues, Thorne published a paper showing that wormholes were, in principle, allowed by general relativity. The paper was written partly in response to a request from the science fiction writer Carl Sagan, who needed a realistic way for characters in his novel Contact to travel between stars. Thorne obliged with a rigorous mathematical treatment. The physics said wormholes can exist. The physics also said they are death traps. A natural wormhole, formed by the raw mathematics of Einstein's equations, is wildly unstable. The moment anything with mass enters the opening, including a single photon of light, the wormhole constricts and collapses. The entry point pinches shut. The exit point pinches shut. The tunnel in between crushes whatever is inside with the force of a collapsing star. Crossing time, less than a trillionth of a second. Survival chance, 0. Worse, even without anything entering, the tunnel radiates its own destruction. Tiny random fluctuations of vacuum energy at both ends grow as they ricochet through the throat. Within an instant of forming, the quantum feedback tears the wormhole apart. To keep a wormhole open, Thorne calculated, you would need exotic matter with negative energy density. The same ghost that haunts the warp drive. Enough of it, threaded around the wormhole throat like scaffolding to hold the tunnel against its own gravitational urge to collapse. How much negative energy? Enough to equal the mass of our nearest star, converted entirely into the exotic substance. Every wormhole big enough to let a person through would require negative energy equivalent to an entire star. Many stars for a stable long-term bridge. Some physicists have suggested that the universe might contain natural wormholes already, left over from the Big Bang, held open by primordial fields we do not yet understand. Telescopes have searched for their gravitational signatures. None have been found. A few anomalous objects have been proposed as candidates, including a distant galaxy showing strange lensing patterns, but nothing has been confirmed. The wormhole for now remains the cruelest kind of dream. Possible on the page, impossible with any material humans have ever touched. Even if a team managed to build one, a second problem would arrive immediately, a problem that strikes at something deeper than physics. A problem that breaks the logic of reality itself. Because a wormhole, properly built, lets you travel not just through space, but through time. And time, if you can jump backward through it, stops making sense entirely. A physicist named Frank Tipler at Tulane University noticed a disturbing pattern in the 1970s. Every method anyone had proposed for faster-than-light travel, when the math was fully worked out, allowed the same impossible thing: travel backward in time. This is not a metaphor. The equations of special relativity contain a direct geometric relationship between space and time. The faster something moves, the more the two mix. Push any object faster than light, and the math tips the relationship past a boundary, letting the object arrive at its destination before it left. Not by much at slow speeds, dramatically at high speeds. A ship moving at 2 times light speed across a 10 light-year distance would arrive several years before its launch. The Alcubierre warp drive, when carefully analysed, has the same property. Thread together a few warp bubbles in the right sequence, and a determined pilot can return home before leaving. The wormhole has it too. A stationary wormhole is a shortcut through space. A wormhole with one end moving fast while the other stays still becomes, over time, a shortcut through time as well. Enter one end on Tuesday, exit the other end on Monday. This sounds charming until you work through the consequences. A physicist named Matt Visser at Victoria University of Wellington published a series of papers detailing what happens when time travel becomes possible. The results are nightmarish. Picture this: you build a wormhole, you enter it on Tuesday, you exit on Monday, you find yourself Monday morning sitting at your desk. You walk over and unplug your wormhole machine before it can be built. The machine never activates, you never travel back. But if you never travel back, how did you unplug the machine? This is a paradox, a logical knot with no escape. And relativity, when allowed to include faster-than-light travel, generates paradoxes like this by the thousand. Every signal sent faster than light can, in principle, arrive before it was sent. Every reply can outrace its question. Cause and effect dissolve into a tangle of impossibilities. Physicist Stephen Hawking wrestled with this problem for years. In 1992, he proposed what he called the chronology protection conjecture. The universe, Hawking argued, must contain some mechanism that prevents time travel from happening, because allowing it would break the logic of cause and effect. His specific guess involved quantum vacuum fluctuations. As soon as any system got close to allowing time travel, he predicted, a cascade of virtual particles would build up and destroy the system before it could function. Hawking's argument was not a proof. It was a guess, supported by calculations he admitted were incomplete. Other physicists, including Kip Thorne and Igor Novikov, proposed different fixes. Novikov's solution, called the self-consistency principle, suggested that the universe simply does not allow contradictions. Any time traveler would find, mysteriously, that their attempts to change the past failed. The gun jams, the door sticks, the plane is delayed. Reality rearranges itself to prevent the paradox. Both solutions remain speculative. The experiments to test them would require time travel itself, which is the very thing being tested. The deeper implication is that every major proposal for faster-than-light travel, from warp drives to wormholes to hypothetical tachyon engines, comes entangled with this causality problem. Not as a bug, as a fundamental feature of relativity. To travel faster than light is to travel backward in time. To travel backward in time is to break cause and effect. And if cause and effect break, the universe starts unraveling in the most famous paradox ever imagined. 1943. A French science fiction writer named René Barjavel published a novel called Le Voyageur Imprudent. In one scene, a time traveller returns to the past and accidentally shoots his own grandfather before the grandfather has any children. The result, if consistent logic is applied, means the time traveller is never born, which means he never travelled back, which means the grandfather was never shot, which means the time traveller is born, travels back, and shoots the grandfather. The paradox loops forever. Physicists and philosophers have argued about this loop for almost a century. It is the most famous puzzle in the entire field of time travel, and every serious proposal for faster-than-light travel must confront it. Because as we established, faster-than-light travel is, mathematically, the same thing as time travel. 3 major solutions have been proposed. None of them is satisfying. The first solution is Novikov's self-consistency principle. The universe, Novikov argues, does not allow paradoxes. Every attempt to kill your grandfather fails. The bullet misses. The gun jams. The grandfather ducks at the last moment. An ambulance arrives in time. The time traveller slips and falls down the stairs before pulling the trigger. The universe, like a novelist tying up loose plot threads, arranges events so that history remains consistent. You can visit the past, but you cannot change it. This solution makes one terrifying prediction. Free will, as humans experience it, may be an illusion. If the universe enforces consistency, then every choice you make in the past was always going to happen exactly as it did. The time traveller thought they were trying to kill their grandfather. The universe had already decided they would fail. Their actions, their thoughts, their frustration were all predetermined components of a story that could never go any other way. The second solution is the many worlds interpretation, proposed by a physicist named Hugh Everett in 1957. Every time a quantum event could go one of several ways, Everett argued, the universe splits into parallel copies, one copy for each possible outcome. Time travel in this framework does not create paradoxes, it creates new branches. You travel back, you kill your grandfather. In that branch you are never born. The original branch where your grandfather lived continues unaffected. You, the time traveller, now live in a universe where you do not exist, a kind of homeless observer, adrift in a timeline that has no record of your birth. This solution makes its own terrifying prediction. Every choice you have ever made, every accident you ever avoided, every heartbeat of your life has a corresponding parallel version where the opposite happened. Countless copies of yourself, living every possible life in countless parallel worlds. a cosmos bloated with infinite versions of reality. The third solution is Hawking's chronology protection. The universe, Hawking argued, prevents time travel from happening in the first place. The moment any machine approaches the capability, quantum effects destroy it. No paradox, because no time travel. Physicists still argue about which solution is correct. The arguments are sharp, detailed, and mostly unresolvable, without experiments that no current technology can perform. And here is the chilling part. If any of the three solutions is correct, faster-than-light travel looks very different from what engineers have imagined. Under Novikov's principle, any Starship mission that tries to create a time travel paradox will mysteriously fail. Engines will malfunction, crews will fall ill, debris will arrive at critical moments. The universe will sabotage the project from within to protect its own logic. Under Everett's many worlds, a faster-than-light ship might succeed, but the crew returning home would arrive in a universe where they had never left, their own past erased, their families, in their original timeline, still waiting. Under Hawking's protection, the ship would simply never function. Every faster-than-light drive, no matter how elegant on paper, would prove unbuildable in practice. All three answers point to the same haunting possibility. The silence of the galaxy may have an explanation that no civilization ever wants to accept. 1950. Los Alamos National Laboratory, New Mexico. Three physicists were walking to lunch. Enrico Fermi, the Italian-born architect of the first nuclear reactor. Edward Teller, the father of the hydrogen bomb. Herbert York, a young physicist who would later become the first director of the Lawrence Livermore National Laboratory. They had been talking about flying saucer sightings, which were filling the newspapers that year. At some point, the conversation turned to the question of whether life existed elsewhere in the galaxy. Then Fermi stopped walking and asked a question that has haunted astronomers ever since. But where is everybody? Our galaxy contains more than 100 billion stars. The galaxy has existed for about 10 billion years. Even if intelligent life arises rarely, on only one star in a million, that leaves at least 100,000 civilizations that have risen somewhere in our neighborhood. Even if most of them die young, a handful should have survived and expanded. A single civilization traveling at even 1% of light speed could spread across the entire galaxy in about 10 million years, a tiny sliver of cosmic time. Yet when we look up, we see nothing. No radio signals, no laser beacons, no megastructures, no probes, no evidence that anyone else has ever flown. This is the Fermi paradox, one of the most disturbing puzzles in all of science. Dozens of solutions have been proposed over the decades. Some are optimistic, some are catastrophic. Maybe life is rarer than we think. Maybe planets with the right conditions are hard to find. Maybe the jump from microbes to complex multicellular life is so improbable that it almost never happens twice. Maybe civilizations destroy themselves before they reach the stars. Maybe every species that invents nuclear weapons also invents a way to use them. Maybe climate change, pandemic, or some dark technology we have not yet discovered wipes out every society before they can spread. Maybe we are alone in the galaxy after all, a lucky freak of a tiny biological lottery, and the universe beyond our planet is silent because there is nobody else to make noise. And maybe the answer is far simpler. Maybe light speed is the wall that no civilization ever breaks. A physicist named Robin Hanson at George Mason University proposed what he called the Great Filter. Somewhere in the sequence between raw chemistry and galaxy-spanning civilization, a step exists that almost nobody gets past. The filter might be behind us, in which case humanity has already passed it. or the filter might be ahead of us, in which case something is waiting to destroy our chances. The engineering we have walked through in this series suggests the filter might be light speed itself, not a single disaster, a wall, a hard physical boundary that keeps every civilization trapped around its home star. Maybe aliens exist, maybe many of them. Maybe each one is sitting in its own local solar system, looking up and running the same equations we've been running, and maybe all of them reach the same conclusion we are about to reach. You cannot get there from here, not without breaking physics, not without creating paradoxes, not without spending more energy than your entire civilization produces in 1,000,000 years. If that is the answer, the silence of the galaxy is a warning, not a mystery. 100 billion worlds, 100 billion civilizations, 100 billion species looking upward at the same stars, and all of them equally stranded. A cosmos full of prisoners, each in a cell the size of a solar system, forever unable to meet. Some engineers refuse to accept that conclusion. They keep building, and one of them, in the desert of Nevada, actually launched a working Starship engine, July 2021, a classified Air Force facility at Tonopah Test Range, deep in the Nevada desert. Under a moonless sky, engineers from a small company called General Atomics activated a nuclear rocket engine for the first time in a ground test. The engine ran for 20 seconds. It produced thrust. It did not explode. The facility was still standing when the test ended. In the world of a nuclear spaceflight, that counts as a resounding success. The program is called Draco, short for Demonstration Rocket for Agile Cislunar Operations. It is funded jointly by the Defense Advanced Research Projects Agency and the National Aeronautics and Space Administration. Its goal is to build the first working nuclear thermal rocket since the 1970s and fly it in Earth orbit before the end of this decade. A nuclear thermal rocket is not a Starship engine. It is modest compared to the fusion drives of Dedalus or the light sails of breakthrough Starshot. But it is real. It is funded. It is being built right now. The design is elegant. Inside the engine sits a small nuclear fission reactor. Liquid hydrogen stored in the fuel tanks is pumped through the hot reactor core. The heat flashes the hydrogen into a superhot gas. The gas rushes out a nozzle at the back, producing thrust. No chemical combustion. No need for an oxidizer. Just pure thermal expansion of hydrogen, heated to temperatures that would melt any chemical engine. The result is a rocket about twice as efficient as the best chemical engines ever built. A ship using nuclear thermal propulsion could reach Mars in 3 months instead of 6, or Pluto in a decade instead of 10 centuries. Not a starship, but the first real step toward one. The technology is not new. In the 1960s, a program called NERVA, short for Nuclear Engine for Rocket Vehicle Application, tested nuclear thermal rockets in the Nevada desert for years. Engineers fired the engines repeatedly, running them for hours, refining the designs. One version produced more thrust than the main engines of the space shuttle. Then, in 1973, the program was cancelled. Budget cuts. Political nervousness about flying reactors in space. The engines were mothballed, the scientists scattered, the knowledge slowly forgotten. A generation of propulsion expertise walked into retirement and took most of the institutional memory with it. Draco is the revival. The engineers leading the program have studied the old NERVA files, updated the reactor designs with modern materials, and added safety features the original designers could only dream of. The reactor will not go critical until the spacecraft is far from our planet. Shielding will protect astronauts during crewed missions. The hydrogen fuel will be stored at temperatures colder than interstellar space. If Draco succeeds, it will prove that nuclear propulsion works. A working nuclear engine in space changes every calculation in this series. Mars becomes a weekend trip. Jupiter becomes a summer vacation. The outer planets, which currently take decades to reach, become months away. The Starship comes later. Nuclear thermal is too weak for interstellar flight on its own. A ship fleeing our solar system needs fusion, or antimatter, or some drive we've not yet invented. But without a working nuclear engine first, every fusion design and every antimatter plan remains trapped on paper. Draco is the first shovel turned, a small engine running in a desert, producing a few minutes of thrust in a test, and a message to every physicist who ever said starships were impossible. The engineering is starting. Meanwhile, another real engine has already been flying for decades, quietly pushing probes across our solar system at a speed so gentle it feels like cheating physics. October 2018. A spacecraft called Parker Solar Probe was climbing toward its close encounter with our closest star. Its main engine was not a roaring chemical booster, not a nuclear reactor, something quieter, smaller, producing so little thrust that you could stop it with your bare hand. An ion drive. Ion drives are real, working engines, flown on more than a dozen missions over the past 30 years. The Deep Space One probe, launched by the National Aeronautics and Space Administration in 1998, was the first. The Dawn spacecraft, which orbited 2 asteroids between 2007 and 2018, used ion drives for its entire mission. The Hayabusa probes from the Japanese Space Agency used them to reach and return from asteroids. Several commercial satellites now use ion drives for station keeping. The engine is almost suspiciously simple, a tank of xenon gas, an electric field that strips the electrons off each xenon atom, turning them into charged particles called ions, a magnetic field that accelerates the ions out the back of the engine at speeds of about 50,000 miles per hour. The ions shoot out. The ship drifts forward in the opposite direction. The thrust is tiny, about the force of a single sheet of paper resting on your palm. A car engine pushes harder than a large ion drive. You could lift a working ion thruster off the ground with one finger. The advantage is endurance. An ion drive can run for years, pushing gently but constantly. While chemical rockets burn for minutes and then coast, an ion drive burns for months, accumulating velocity a sip at a time. Over long enough timescales, the gentle push becomes enormous. Dawn used its ion engines for more than 5 years and reached a total velocity change greater than any other spacecraft in history. For Starship travel, though, ion drives hit a wall of their own. The xenon fuel is expensive and limited. Every pound of propellant a ship carries must be produced on Earth and hauled up to orbit at great cost. And even with the largest possible fuel tank, an ion drive ship tops out at a few % of the speed of light. A team at the Jet Propulsion Laboratory calculated the travel time for a modern ion drive spacecraft to reach Alpha Centauri. Their answer: about 18,000 years, less than the 75,000 years of a chemical rocket, but still longer than all of human civilization. Newer versions might do better. A design called the Casimir drive, developed by a former astronaut named Franklin Chung Diaz, uses radio waves to superheat the ion exhaust, producing stronger thrust with higher efficiency. Tests in the laboratory suggest Casimir could reach Mars in about 3 months, a major improvement. For interstellar travel, it would still require thousands of years. The fundamental limit of any ion-based engine is called specific impulse. The higher the specific impulse, the faster the exhaust comes out the back, and the more efficient the engine. Ion drives have the highest specific impulse of any working engine, but still limited by the need to carry fuel. A ship at the theoretical maximum ion drive performance would need a fuel tank larger than itself for a voyage of even 1 light year. A handful of exotic proposals try to push past this limit. Nuclear electric ion drives, where a fission reactor powers a much larger electric field. Plasma drives, where the ship rides its own electrified exhaust. Particle beam engines, where heavy particles are fired at relativistic speeds out the back. None of these has flown. All of them remain on drawing boards, waiting for the day when someone can afford to build and test them. Meanwhile, ion drives continue their patient, gentle work, pushing probes across our solar system at speeds that would take millennia to cross the gap between stars. There is one more engine design worth visiting, one that skips the fuel problem entirely, the same way breakthrough Starshot does, but with a twist that might actually work. Santa Barbara, California. A laboratory on the campus of the University of California, where a physicist named Philip Lubin has spent the last 2 decades designing what he calls the only realistic way to reach another star within a human lifetime. His plan: build a laser array so large and so powerful that it can push a spacecraft not by carrying fuel, but by shining light at it. Lubin's program, called Directed Energy Propulsion for Interstellar Exploration, is the scientific backbone behind breakthrough Starshot. His team has spent years working out the math, the materials, the geometry, and the economics of a ground-based laser capable of firing a probe to relativistic speed. The science is simple. Light, despite being massless, carries momentum. Every photon striking a reflective surface gives the surface a tiny kick. A solar sail catches sunlight and uses the kick to push a spacecraft. A laser sail does the same thing, except with a much brighter, more focused beam. Aim a powerful enough laser at a lightweight sail and the sail accelerates. Scaling the idea up is where the engineering gets breathtaking. A laser strong enough to push a probe to 20% of light speed would need to produce about 100 gigawatts of continuous power. That is more power than every nuclear reactor on Earth, combined, pouring out of a single installation in a desert somewhere, focused through thousands of individual laser elements working in perfect harmony. Lubin's team has demonstrated small-scale versions in the laboratory. Arrays of synchronized laser diodes, coherent over distances of meters, have shown that the basic concept works. Scaling from a laboratory bench to a mile-wide array in the desert is a matter of manufacturing, cooling, and power supply, none of which violate physics, all of which demand vast amounts of money and time. The advantage over every other Starship design is that the fuel stays on Earth. The ship itself carries almost nothing. No fuel tanks, no reactor, no engines, just a sail, a chip, and a few grams of supporting structure. The acceleration happens during the first few minutes of flight, when the laser array hits the sail hardest. After that, the probe coasts the rest of the way to its destination. The ship can be small, the ship can be simple, the ship can even be expendable. If one probe out of 1,000 fails, who cares? Launch 1,000 more, aim a few at each of the nearest stars, spray the local stellar neighborhood with a swarm of postage stamp probes, each one snapping photos as it passes. Lubin has calculated the cost. A full-scale laser array, capable of launching probes to Alpha Centauri, would cost roughly $10 billion and take about 2 decades to build, comparable to a major particle accelerator. Cheaper than a long war. A reasonable investment if any government decided to make it. The United States government has not. No government has. The program remains primarily privately funded through breakthrough Starshot and a handful of research grants. Progress continues slowly, paper by paper, experiment by experiment. The laser array is not yet being built. The sails have not yet been tested in space. The chip-sized probes remain prototypes in clean rooms. Lubin himself is optimistic about the timeline. He has stated in public lectures that a working laser-driven probe to the nearest star is, in his view, achievable within the lifetime of a child born today. Other engineers are less hopeful. The sail problems, as we covered, remain unsolved. The dust problems, the radiation problems, the navigation problems all wait at every stage. Still, Lubin keeps designing. Every year the drawings get sharper. Every year a new barrier falls. The math, which once said interstellar travel was impossible, now says it is merely expensive. Which brings us to the final question. The one every physicist, every engineer, every dreamer eventually has to face. Will humans ever reach another star? You're back in the command chair. The simulation is over. The ship, the dust, the laser, the wormhole, all of it was a walkthrough of what the math actually permits. And now, with every equation laid out, every program listed, every engineer quoted, a single question remains. Will humans ever reach another star? The honest answer is a cold engineer's answer. Maybe. And if yes, probably not the way science fiction promised. Faster than light travel, for all its elegant mathematics, collides with causality. A warp drive that exceeds light speed creates time paradoxes that the universe may simply not allow. A wormhole big enough to carry a ship requires negative energy in amounts that no one has ever produced, or even demonstrated. Every serious attempt to break the speed of light runs into a physical barrier that looks, increasingly, like a fundamental law of reality, not a problem engineers can solve with better materials or bigger budgets. Slower than light travel, the kind that obeys relativity, remains possible, barely. The engineering is brutal, the timelines are punishing. Every design in this series, from Orion to Dedalus to Longshot to Starshot, concludes with the same verdict. Building the ship is technically feasible. Building the civilization that can afford to do it is the harder problem. A probe to Alpha Centauri, arriving in a human lifetime, is within reach. Lubin's laser program could launch one within 50 years if a government decided to fund it. The probe would not carry humans. It would not stop at the target. It would fly past, snap photos, and vanish into deep space. A postcard from the nearest star arriving decades after its sender had died. A consolation prize for a species that once dreamed of walking on other worlds. A crewed mission is harder. Every obstacle we covered, the fuel equation, the radiation, the navigation, the dust, the blue shift, the silence, the body, the psychology, remains unresolved. No single one is impossible. All of them, stacked together, make the mission a generational planetary, perhaps species-level effort. The kind of project that would take centuries of stable civilization to complete. Humans have never sustained a stable civilization for centuries without interruption. Some physicists believe we will still do it. A team at Tau Zero Foundation, the descendants of the breakthrough propulsion physics program, continues to publish papers arguing that within 200 or 300 years, the technology will exist. They cite the history of progress. From the Wright brothers to the Apollo program took 66 years. The distance from Apollo to a realistic starship, they argue, is roughly the same. Other physicists are less hopeful. They point to the Fermi paradox. The galaxy is silent. If starflight were easy, somebody would have done it, and we would see the evidence. The silence, they argue, is telling us something. Maybe the barrier is higher than we think. Maybe every civilization hits the light speed wall and stops, just like ours is stopping now. The truth, like most truths about deep space, is probably somewhere between the two camps. Humans may build interstellar probes within a century. Humans may never send a living crew beyond the edge of our own solar system. Our great-grandchildren may receive data from Alpha Centauri. They may also spend their whole lives, as every human before them has, looking at the stars and wondering. Here is the final fact, the one that survives every objection and every calculation. Every time humans have been told something is impossible, we have eventually done it. Not always, not quickly, not cheaply, but often enough that any prediction of permanent failure sounds more like a warning from within the cage than a measurement of the bars. The speed of light is a wall, the rocket equation is a wall, time dilation is a wall, negative energy is a wall, and a species once told it could never fly learned, in a single century, to build machines that reach the moon, land on Mars, and photograph the edge of our own galaxy. Somewhere, perhaps, a child is being born today who will one day stand on a beach around another star, pick up a handful of alien sand, and look up at a sky nobody from Earth has ever seen. Or perhaps not. The engineering does not promise. The engineering only says, this far, no farther, unless you build something we have not yet built, pay a price we have not yet paid, and cross a wall we have not yet crossed. The stars are waiting. The math is ready. The rest is up to us.